So welcome to the tutorial on probabilistic circuits. So this tutorial was presented at UCLA in the CS201 seminar on May 12th and May 14th. It consists of two parts. The first part is on inference and representations. And so this part will be presented by Antonio Vergari, who's a postdoc at UCLA, and then myself, Ivan den Broek, who's also a faculty at UCLA. And then the second part about learning and theory of probabilistic circuits will be presented by Robert Pehaers from TU Eindhoven and Yu-Jung Choi, who's a PhD student at UCLA. And so both of these recordings from the two separate days are concatenated into this longer video. So enjoy. Why would you care about this tutorial? Well, if you've been studying probabilistic models in AI, things get confusing really quickly. So already in your undergraduate AI or machine learning course, you probably heard about things like naive Bayes, Bayesian networks, vector graphs, probabilistic graphical model, things like junction trees. If you studied some machine learning recently, you've heard of generative adversarial networks, variational autoencoders, all sorts of deep generative models. And so it's really a mess, the kind of landscape of probabilistic models in AI. And so the goal of this tutorial is to help you make some sense of this alphabet soup. And we'll focus a lot on the question of whether these models are tractable or intractable. And so Antonio will precisely define what that means. But you know, you can already easily distinguish some of these models we'll talk about as being tractable, meaning they allow you to compute certain things exactly and efficiently, versus a lot of other models that are representations of a distribution, but you cannot really use it to efficiently get answers to your queries. But then what we also want to definitely get across as a main point, main takeaway of this tutorial is that this tractability is really a spectrum. So there are models that are extremely tractable for reasoning, and there's models that are extremely intractable because they don't support any types of queries. But there's a huge spectrum in the middle, and we can easily characterize the spectrum by looking at properties of these models. So we'll try to explain that really there's only a few key ideas here that allow you to understand what these models are able to do and what they're not able to do. And then from a machine learning or modeling point of view, you also care about how expressive are these models. So even within models that are tractable, that allow you to answer certain queries, some of them are very limited in what they can express, and they make some serious compromises in terms of what you can represent in order to allow for the tractability, while some of the models that we'll talk about will actually be very expressive while also giving you certain guarantees. So that's kind of the big picture. Let's make sense of this alphabet soup. And so, especially for these tractable models, we'll try to present to you a framework to think about them that is somehow this umbrella concept of probabilistic circuits that captures all of these things. And it's easy, once you understand what a probabilistic circuit is, you can look at any of these other representations in the AI literature and the machine learning literature and understand their tractability properties. So that's the schedule for today. Antonio will talk to you about why do we care about tractable inference, what is it, and what are the trade-offs involved with the existing models. And then I will talk about this framework of probabilistic circuits, what are they and why are they tractable. And then Robert on Thursday will talk about the machine learning side of things, how do you learn them from data, the structure and the parameters of these models. And then Yu-Jung also on Thursday will talk about more advanced issues with these representations, how you translate between them, how you connect them to certain more advanced models, how you do some very complicated queries, and also how you study them from a theoretical point of view. So I should say, if you have questions, I have the Q&A box open, I have the chat box open, I also have the list of participants open, so if you raise your hand, I will allow you to talk, and then you can just interrupt with a question. So I'll try to monitor all of that. Okay, so that's the setup. And so next, Antonio will talk to you about why tractable inference in the first place. So Antonio, if you share your screen.
Yes, thanks, Guy. Let me try. Okay. I hope you can see my screen. So my job is like to introduce what's tractable inference and like tell you why you should care about tractable probabilistic inference. But To begin with, let me argue why we need probabilistic models and probabilistic inference in the first place. So here is one example for you. So suppose you are like a decision maker and you have to manage like the mobility of the whole city of Los Angeles. So you may ask yourself, what's the probability that today is a Monday and there is a traffic jam on Westwood Boulevard? Maybe you're just like a student and you just want to know like which day is most likely to have a traffic jam on my route to UCLA campus. So you're a decision maker, you have to take like a decision in the real world, and the real world is full of uncertainty. And to take these decisions, you might get like some aid by trying to answer to these questions. And we say that this question can be mapped to something we can compute, something called probabilistic queries. But how do we do that? So we want to answer these kind of questions. And since we are like data scientists or we do machine learning, we generally have at our disposal a bunch of data. And this data comes like with a bunch of like data samples that are rows and columns that are some attributes or features. In our case, like random variables. So we might want to use this data to answer these questions. So what can we do to begin with? Well, we're going to fit like a predictive model, of course. So this question usually might come in a flavor when we have some inputs and some outputs. And in this case, like the output is street and the input is like some attributes about like the time. So we're going to fit like, let's say, a classifier or a regressor. We're going to take just a bunch of samples from our data, some rows that are talking about like our inputs, the feature we are conditioning on. And then we're going to just like learn out of that. And then we're going to use this, right? Just going to fit predictive model and we're going to answer all our questions. Well, it's more complicated than this. We're not going to use like predictive models. And the reason is why, because like maybe next time you're going to ask like a very different question that's going to have like the very different inputs and outputs. So you need to retrain a different model, a different classifier. Might be a neural net, might be like a decision tree, but it's going to be different from the previous one. And you have to do that for every possible questions. Moreover, at a certain point, you might ask some question for which like there is really no row in the data you have collected so far that's gonna get you like an answer. So that there could be that there is no street, you have not observed that data yet, or you do not have enough label for that. So this is not clearly the route. Some other times, you do not even have a very clear like distinction between what's input and output. You're just interested into modeling the uncertainty over states of the world. May they talk about all the attributes or some of them, like in this case. So we're not going to use predictive models. We're not going to use classifiers or regressors. We're going to use like probabilistic generative models. We're going to have a single model that's going to encode the whole joint distribution for all the attributes in our data. And we're going to bomb this single model by lots of kind of different questions. So lots of questions by the single model. So if you want, in a sense, this single model, which encodes like the joint probability distribution, is going to capture all possible patterns that are there in the data. And this is what we usually do when we do, for instance, exploratory data analysis, which is a clear unsupervised learning task. So let's get back to the original example and let's try to formalize this such that you get a better intuition of what I'm talking about. So you're questioning, you're asking, what's the probability that today is a Monday and there is a traffic jam on Westwood Boulevard? So to formalize this, we need to name our attributes, our features. So we have a bunch of random variables, one for the day, another for the time, and a collection of, let's say, binary indicators, one for each street that we might think of. And each one of these indicators just is set to 1 if we have a jam, a traffic jam on that street. So to answer that query, we just have to compute the probability of this event, that today, the random variable day is set to Monday, and that the indicator variable for like the jam on Westwood Boulevard is set to 1. We don't care about the rest of the variables. So in a sense, we are marginalizing them out. On the other hand, if you look at the other example of the second question, the second query, we have to do something different. So we are interested in which day is the most likely to have like a traffic jam on my ride to campus. So definitely, as before, we have to marginalize something out because we are not interested to a specific time, and we are not interested to the value of the indicator variables for some of these like streets. And we want to perform maximization over the variable day. We want to get like the most likely day. Moreover, we are putting like a certain form of like evidence which involves like some complex logical event. In this case, like represented as a disjunction over all the streets that appear in my route to the campus. So we're gonna do like a little bit of marginals, map queries, which I'm gonna introduce later more specifically, and some form of logical events. So to perform probabilistic inference, we need to answer this kind of queries. And as you have seen so far, some of these do share some structure. So we can group them into classes. Now the question is like, what's like tractable probabilistic inference? Well, in a sense, we would like to answer these queries efficiently. But more formally, let me introduce this. So we say that a family of models, of probabilistic models, is a tractable representation for a class of queries, Q, if for every query that I pick from this class, I'm able to compute each result, its output exactly with respect to my model in polynomial time with respect to the model size. And the concept of the model size is going to vary a bit. We're going to see like a bunch of like model classes now, and you're going to get a flavor of what it is. But in general, this poly time is going to be like linear in the size of the model. This is like good. Moreover, the size of the model is going to be like a polynomial into the size of the input, which you can think about like the number of random variables that you're talking about, or big data domains are. And this is also good. But so far, I'm like just focusing over like exactness, right? But why do we care? Why don't we go for approximate probabilistic inference? Well, because exactness is going to provide us like the best guarantee possible, and because we know that we are computing the correct results. In some approximations, we might not even have like guarantees of this kind. We do not know how far we are from the true solution, and this might be problematic if we want to use probabilistic inference to enable and support decision making in the real world. So what I'm going to do for the rest of like this part is like to go and show you like a bunch of like query classes to motivate how they can support decision making, and I'm also like go through like many of the classes of probabilistic models that you might know from your studies or from your research, and I'm going to argue like if they are tractable with respect to the query classes we've seen, and if so, like how expressive they are. And later on, Guy is going to introduce like probabilistic circuits as a unifying framework under which you can put like, you can factorize many representations of this kind. So let's begin. And I'm going to fill like this sort of table. I'm going to put like as columns like the possible query classes into this queue, and as rows of this table like the possible model classes that I'm going to show you. At the intersection, I'm gonna just like keep track if this like model class is like tractable for that query class. So let's see. From the simplest class of query that you can think about, like complete evidence queries. So suppose you want to answer this question: what is the probability that today is a Monday at noon, and there is a traffic jam only on Westwood Boulevard? So clearly, I am providing like a complete assignment. For all of the random variables in my collection, I have a value. So day is assigned to, Monday is assigned to day, 12 is assigned to time, and then all the indicator variables are set to 0 with the exception of like the one for the traffic jam and at Westwood Boulevard. So I want to compute like this, the probability of like this complete configuration, complete assignment or evidence, if you want. And this might seem like a very simple, a very trivial class of queries, but we use that a lot of time when we perform learning, specifically maximum likelihood learning. So when we want to learn our probabilistic models from data, we basically select the parameters that are maximizing the likelihood of the data that we're seeing, like in our training data. So this is like a very simple class of queries we might be interested in like solving. So what's the simplest or one of the well, which kind of probabilistic models shall we use to answer these queries? Well, of course, it's like 2020, and we need to use like generative adversarial networks. And I'm pretty sure that many of you have like known this framework. So we're gonna have like these two neural networks, a generator and discriminator, and they're gonna play this min-max game until some convergence. And we're gonna solve like this, like complete evidence queries, right? Well, not really, because generative adversarial networks are not even like explicit likelihood models. We don't even know how to like write it down, the likelihood of this model. So we cannot do that. So they are intractable with respect to compute like complete evidence queries. And yeah, someone could say, yes, sure, but we can like still like approximate them by performing Monte Carlo estimates by sampling lots of samples. But it's also quite troublesome because we're gonna need like lots of samples. They're gonna like face mode collapse and all the pesky issues that people that's dealing with generative adversarial networks are trying to do. So we cannot really use GANs for doing like this even simple, very simple like probabilistic inference scenario. And again, so if you are into probabilities, probabilistic models, if you are not using GANs, you must be using like VAs. So variational autoencoders. Variational autoencoders are like better than GANs because now we have like an explicit likelihood model. And this likelihood model is in essence like a mixture model over one infinite and uncountable set of mixture components. And we have to solve like this integral to do that. So can we solve like complete evidence queries with variational autoencoders? Unfortunately, no, again, because we cannot compute like the probability of a joint assignment exactly. We need to resort to a lower bound, the elbow. And to perform like learning and inference with the elbow is quite tricky. There are many issues over there. So we're gonna discard also variational autoencoders. And this is like what we're gonna put in our table. Two rows, the two most prominent, let's say, model classes, at least like hype-wise in the probabilistic modeling community, GANs and VAs, which are not even able to compute exactly an intractable way then this very simple class of queries, complete evidence. So what's left? If we cannot use GANs and VAs, we must be using normalizing flows. Normalizing flows in essence are just like an invertible mapping, a bijection F, that maps like latent space, let's say Z, with the space that we observe, X. And we generally assume that the space Z is distributed according to a simple distribution, let's say isotropic Gaussian. And instead, the space X is the space of our like features and attributes, and that's very complicated, the true distribution over there. However, we can compute, in this case, like the joint probability distribution by the change of variable formula. So in essence, we just have to compute the probability of the distribution in the space of Z according to our like inverse bijection, and then we have to correct this term by like the determinant of the Jacobian of this invertible transformation. So if we assume that there is some structure into the Jacobian, for instance, like it's diagonal, we can compute this determinant exactly and efficiently, right? So we are able finally to compute like complete evidence queries. So we found like the first model class that might be usable for our purposes. And this has been used in the recent literature a lot. There are lots of variants for this, including also autoregressive models. So we found
so
like
there's a question in the Q&A. What is EVI? So EVI is the probability of a complete state.
Yes, let me go back. So that's our definition. So yes, it's like the probability of like a complete state. So you assign some value to all the random variables that you are like considering in your distribution. And you could also like try to compute like probability masses or probability densities, or if you have like a mixed probability mass and density function, you can compute that. Yes. Does this answer the question? It's tricky. So for instance, in this case, we want to compute this P of X that you can see up. And to compute that, we have to compute like the P of Z of like the value provided by the inverse of this transformation. And we have to multiply like the determinant of the Jacobian of the transformation. And we can do that. Suppose that the Jacobian is like easy to manipulate. So we can compute like complete evidence queries. Let's move to the next class of queries. And the next class of queries is going to be like marginal queries. So with respect to the previous like example, now we're just interested into the probability that today is a Monday and there is a traffic jam on Westwood Boulevard. This is our initial example, right? We don't care about the time. We don't care about all the other streets. So in general, we just set like a subset of our random variables. Let's say we provide some values for that, and this is our partial evidence. This is the set E. And for the remaining ones, let's say H, we just need to integrate over their possible values. Or if they are like discrete, we need to sum over all possible cases. This is like marginal queries. And if you are able to solve like marginal inference in an exact and efficient way, then you can do also do conditional queries, because in essence, conditional probabilities are just like this ratio. So you have to first compute like some giant distribution and then divide like by this normalization factor, which is like a marginal. And marginal queries are like ubiquitous, because you can think about like just dealing with missing values in your data. Or if you want to some fancier application, here is one for you. So suppose you want to do scene understanding, that is, try to understand what are like the objects and the relationship in your scene represented as an image, so as like a bunch of pixels. So many of the models that are out there really need to take care of like what's in the foreground and what's in the background. But what's in the background really doesn't provide much information most of the time. So you could marginalize it out. So if you have a model of just like some subroutine in a larger like algorithm that provides exact marginals in tractable time, you can speed like scene understanding, and you can also have like better accuracies. So I'm putting here like just a bunch of like references for some works exactly doing this for the models that, with the models that Yi is going to introduce later. So let's go back to normalizing flows. So we know that normalizing flows allow for tractable evidence queries. Do they allow also for tractable marginals? Unfortunately not, because we cannot easily perform the integration that's like is needed for computing marginals in this models. Even if we could, like, let's say you have like a constant volume, so the determinant of the Jacobian is not really important. We need to integrate over the bijection. And if we have like a very simple bijection, maybe if it is like the identity, we can do that. But this is really not an interesting class of models. So we cannot do this with flows. So here is a recap. So we've seen like complete evidence, marginals, and conditionals. And so far, flows only provide like tractable inference for evidence. What's the reason behind this? So to try to understand that, let's zoom out a bit. Let's go into the classical framework of probabilistic graphical models. So for probabilistic graphical models, under which we could also describe the previous models, in a sense, also VAEs and flows, we have this very neat distinction between representation and inference. So we can represent a complex joint probability distribution through a graph formalism. And in this graph, nodes are our random variables, and the edges between them do encode their dependencies, or if you want, their independencies. Then once you have like this representation, this structure, you can pick the algorithm you want, and we have a bunch, we have many for PGMs, and then you can perform inference over that. That means that you can try to solve the queries that you are interested into. So can we do like more in PGMs in general? Well, in general, no, because the complexity for exactly compute marginals it's shocking hard. So we cannot do that. And this is one of the striking cases when if we want an approximate solution with guarantees, that's also a hard problem. So we cannot do that. So what's the reason behind this? The reason behind this is that because we have to deal with the tree width of the model. And doing marginals is exponential in the tree width. What's the tree width? You might not know, but if you have like a PGM in a sense, which is a graph, you couldn't try to decompose that as if it looks like a tree by grouping like variables together. So if among all possible ways that you have to decompose this as a tree, you have to pick like the way that provides you like a cluster of variables where you contain all these nodes, and this is like the minimum of the largest ones ever. So in a sense, it just tells you like how far is one graph from being reshaped from a tree, how hard it is. So this concept of a tree width also provided a very interesting like take on tractable probabilistic inference, because since like the inference is exponential in the tree width, what if we fix the tree width to a value that makes inference tractable in practice? This led to lots of interesting representations in the literature. So we can have like trees, polytrees, junction trees that have to be thin, such that you cannot put many variables together. And if you keep the value of the tree width to a reasonable level, let's say 20 or even more, you can perform exact inference here in this case. I'm going to focus on one of these models, one of these low tree width or bounded tree width PGMs, and this model class is trees. And trees are very interesting because like not only you can perform like exact probabilistic inference for complete evidence, for marginals, for conditionals, in times linear in the number of variables. And you can do that because, as you can see here, we just need to just multiply together all these small probabilities of one variable given its single parent. And it's a single parent because it's a tree. But we can do something more. We can also do exact learning by the classical Choyu algorithm. That is, we can learn from data what's the best tree that better approximates like the true probability distribution that generated our data, what we're really interested in. We can do this in quadratic time. So trees are very interesting models. So let's stick with trees, because with trees seems like we can answer like complete evidence queries, marginals, and conditionals. So they really are the best. So it seems like that's a very like simple model class, and a not so recent one can really like provide something that more recent models cannot do. So where is like the trick? There must be something going on, right? What do we lose? Well, to be honest, if we stick to trees, we're not able to represent all possible distributions, right? This is evident because like we are not allowed to put all the edges we want in this graph. We need that to be a tree. And by this reason, it's true that we're not able to represent a distribution, for instance, where we have like a connection between x1 and x4. So these models are not expressive enough. Is there a solution, a simple solution for this kind of like situations, such that we can still retain like tractability but increase expressiveness? And the answer is positive, is yes. And this is like the solution, mixture models. So mixture models just take like a bunch of different like simple and tractable models and put them together in a convex combination, like in this case. So look at here. We are putting into like a convex combination two Gaussian distributions. Each Gaussian is not able to model a distribution that has more than a single mode. But when we put them together, we are able to model this bimodal distribution in orange. And with mixture models, we are able to compute complete evidence, marginals, and conditionals in time by paying a small price, which is just like scales in the number of the components of the mixture. So mixtures are very, very appealing. Before moving to what are like the properties for concerning the expressiveness of mixtures, let me point out that whenever we have a mixture models, we have like a latent variable model. And the latent variable here is a categorical variable that has as many states as the components of the mixture, like in this case, 2, one for each Gaussian in our mixture. And in essence, it acts like a switch. So basically, it says like which components we are selecting in this case. And the weight of the mixture model is basically the prior probability that this categorical latent variable Z in this case takes that value. So this is going to be like very important because for now it's the secret that lets us like increase expressiveness, and later on it's going to be like something we need to pay attention to when we compute like more sophisticated queries. So why is this interesting? Because like we by adding more components, we are able to represent more complex distributions. So it is a very well-known fact that a mixture of Gaussians with enough components can approximate well any possible densities. This is true, but potentially, ultimately, we might need lots of components. So this kind of reasoning really holds like asymptotically. Can we do better? And can we ask like really, how many components do we need to approximate in a good sense some distribution? So we need not to look at expressiveness per se, but expressive efficiency or succinctness. It is the ability to represent like a large class of complex models, but compactly, like with not so many parameters, not in a wasteful way. So on Thursday, Eugene is going to define this like properly. I'm just like keeping this as a high level, but to provide you an intuition of why this like is important, or why like simple mixture models, shallow mixture models are not that expressive efficient. I'm going to show you like this cartoon. So we have here like 4 kinds of simple 2D densities, like the multiple ring densities, the funnel density, or the banana density, or the sign density. So how many Gaussians do we need to approximate these densities well? If we use just 2 Gaussians, well, we're not doing a great job, right? We can do better. So what about like 10 Gaussians? For the banana, maybe we're getting like the shape in a sense, but for the others, that's not the case. At least for the concentric rings, seems like we're getting like a donut density. So that's far from optimal, right? So we really need like hundreds of Gaussians to approximate this distribution as well. And this might be wasteful. So let's say that shallow mixture models are not that expressive efficient. So the key idea that's gonna like pop up later would be like to stack different mixtures one on top of the other to be more expressive efficient. But so far, mixture models have a very powerful class of models, and they are like providing like tractable inference for complete evidence, marginals, and conditionals as trees, but they are more expressive than trees. So we're gonna stick like to mixture models so far. They're definitely the best model class we've seen so far. So let's move to the next class of queries, maximum a posteriori map queries. In this case, we want to maximize some probability, and we want to retrieve some state for some variables that maximize that. For instance, you might ask, which combination of roads is most likely to be jammed on Monday at 9 a.m.? So we want to retrieve the vector, the configuration, the giant configuration for all our like indicator variables for the traffic jam for all our streets, given that we set that the day is Monday and the time is 9 a.m. We want to perform this maximization, and in general, we have like some partial evidence maybe, and we want to compute like the most probable assignment for the remaining set of variables, Q, like in this case. So if this is like a definition for our class of queries map. Can we do this for mixture models? Unfortunately not, because recall, a mixture model, nothing but a latent variable model. So we need to marginalize out this categorical latent variable, which means we have to sum over all possible values of z. Since we have like to perform maximization over summation, we cannot try to like swap them and try to like perform maximization only over the components. So in general, map is intractable for mixture models. Before getting like to our table, let me just like provide like another cool application for which like map probabilistic inference is meaningful indeed. And this goes under the name of like imaging painting, if you know a little bit about like computer vision or also computer graphics. So in this case, we would like to observe like any part of an image, but only that part, and we would like provide like a reconstruction for all the remaining pixels. And there are a bunch of models that tried this, providing like map inference in one exact fashion, flavor, or even with approximations. But back to our table. So this is so far like where how far like mixture models can really take us. And this is maybe like a very clear slide that tells you like what's the trade-off between tractability and expressiveness. Tree models are able to compute map in an efficient way. Mixture models, no. Tree models are not as expressive as mixtures. So this tells us like the story that we have to trade off tractability for expressiveness somehow. And seems like we have to go back to trees, right? And let's move to another harder class of queries, that is marginal map. So as before, we want to know like what's the combination of roads that is most likely to be jammed at 9 a.m. But I'm not interested into like the day, so I'm going to marginalize that variable out. This is like the formalization of our example, and more generally, we're going to provide some partial evidence over some random variables E. We're going to query about another bunch of random variables Q, and the remaining ones are the variables we do not care. So those are the ones that we're going to like sum over or marginalize. And the question is now, can we do this for tree models? Can we compute marginal map efficiently? And unfortunately, the answer is negative. So this is a hard task also for trees and very simple models like trees like naive Bayes. So seems like that we also like reached the end of the tractability spectrum for tree models. And this end is like for marginal map queries. This is like somehow sad, even more if we think that maybe in the real world for decision making in the wild under uncertainty, we would like to answer more advanced queries than this, right? More advanced than marginal map. For instance, we might ask like the query that I showed you at the beginning, which day is most likely to have a traffic jam on my route to campus. And this involves like marginals, performing like maximization, and this like logical events. Or we can also try to ask like, what's the probability of seeing more traffic jams in Westwood than Hollywood? This in a sense would require to count and to perform some sort of comparison between different groups, in this case neighborhood, Westwood and Hollywood. And there are a bunch of other queries that are going to be touched in the second part of the tutorial, so I'm not going to spend much time over them. But the fact is that all the model classes we've seen so far are not able to solve like this umbrella query class that I call ADV, advanced queries, right? So this like really lets us think that like, is that the best we can do? What if I tell you there is like a model class that is able really to solve all of this? Well, there is. In this class, it's like fully factorized models. So if we assume that all our random variables are independent, there are no edges in probabilistic graphical model we are considering, we can solve like marginals, marginal map in time linear in the number of variables. And this is like somehow remarkable, but at the same time really tells us that yes, these models are not expressive at all. thinking about independence in this context really requires making like a strong assumption, right? But these models are going to provide the second key ingredients, like to building like more expressive and also at the same time tractable models, like in the second part that Guy is going to introduce in a moment. So this is like the recap table. Some models like factorized are going to able to get you like lots of mileage, others not. The two key ingredients we've seen so far are mixtures, mixture models, and factorized distributions. And you're gonna see like why in this part. But before like leaving the scene to Guy, let me just recap this in a cartoon. So in this 2D plane, I'm gonna put like on the y-axis, on the vertical axis, like models according to the fact that they allow larger tractable bands. That is, like they can answer like a larger set of query classes if we go upwards. And on the horizontal axis, I'm gonna like try to order models such that on the right we can have like models that are more expressive or more expressive efficient, and on the left those that are less expressive. So as a recap, we can put like all these VAEs, flows, GANs, but also general Bayesian networks and Markov random fields on this hortant. So they are expressive, but they are not that much tractable. On the other end, classical PGMs and bounded tree-weight PGMs or fully factorized models do provide you like tractable inference for many classes of queries, but they are not that like expressive or expressive efficient. We would like to be clearly in the positive hortant to the upper right part. And this is where like probabilistic circuits are gonna lead you. And this is also where like I'm gonna switch. So if you do not have additional questions, I'm giving the word to Guy.
Thank you, Antonio. So definitely a good time for questions now. Otherwise, I will take over the screen. I hope you can see this. So like Antonio said, we have this kind of sad picture where everything is somehow intractable or completely inexpressive, right? So this is a very negative story. And now I have the nice job of telling you that Antonio was completely wrong, and actually you can live here in this sweet spot, right? And so that sweet spot will be occupied by a few different types of probabilistic models, but we will characterize them under the umbrella of probabilistic circuits. So let me try to now give you the intuition of what these things are, how you build them, what their properties are. And so I'll mostly focus on what they are and why they're tractable. But then at the very end of the seminar, I will also give you some evidence that not only are they tractable, they're also very expressive and a good fit to your data. Okay, so what's a probabilistic circuit? Probabilistic circuit is some computational graph, and I'll show you specifically what that means in just a second, over the random variables x. And this computational graph is encoding a probability distribution, which is of course the thing we're after. It could be normalized, possibly an unnormalized distribution. Okay, so that's a very vague definition. So let's maybe try to build it up from a few examples. But already to note is that these give you some kind of operational semantics. It's a computational graph, very similar to maybe a neural network that tells you how to execute the thing that it represents if you want to query it. And what will also be key is to look at the properties of this computational graph. As we assume more things, some queries will become tractable. Okay, so this is the outline of the remainder of the seminar. What are the building blocks that give you a tractable probabilistic circuit? And then for which queries are these tractable? And then on Thursday, Robert will start his part of the seminar by explaining to you how these things can be learned from data. And of course, afterwards, Yujang will talk more about the representation and some theoretical questions involved. Okay, so let's look at the simplest possible probabilistic circuit. And the simplest possible probabilistic circuit is just the base case. It's a single node encoding a distribution, and very often we will assume that it's just a distribution over a single random variable. Something very easy from your first statistics textbook, maybe a Gaussian over one variable, maybe some basic Bernoulli coin flip, whatever is the simplest possible distribution you can think of. And so for these little simple distributions, we'll have to assume a few things. Well, here's, by the way, an example of this coin flip. So here I gave you this example of x being a Gaussian, which is a continuous random variable, but x could also be true or false. So you can think of this as a logical literal that gives 100% probability to x being true or 100% probability to x being false, right? So these are other examples of little single variable distributions that are somehow easy to think about. So we'll have to assume a few things about these little distributions. So we'll have to assume that these distributions by themselves are tractable for all the things we care about. So specifically, I assume that for a Gaussian, I can just plug in, let's say, the height of a person and get the density of the Gaussian at that particular point. I will also assume that I can do marginalization on this single distribution. And of course, if you only have one variable, if you marginalize out that variable, meaning you will sum or integrate over all of the possible values of that distribution, if you have a normalized distribution, this output should always be 1, right? All possible worlds have a probability that sums to 1, or otherwise it's called z, the partition function, which tells us the normalization constant of our distribution. And then finally, we'll also assume that these little distributions allow us to compute the map state or the mode of the distribution. So I can figure out what is the highest point in this Gaussian, for example. Okay, so those are a few assumptions about these basic building blocks. And then the way it works is you plug in as input to your node some value of the random variable, and as the output, for example, you get the probability of evidence, the probability of that value or its density. Okay, so this is not really enough. We'll have to somehow include more than one random variable in our distribution. And then, so one of the ingredients that Antonio already mentioned is to use the idea of factorization. So factorization allows us to have all these little distributions over different sets of random variables and combine them into a larger distribution. And so that's exactly what the equation here shows. You can think, for example, if you like, about a multivariate Gaussian with a diagonal covariance matrix. And in that case, all of these little distributions here are univariate Gaussians that you turn into a joint distribution for those 3 random variables together. And so what's nice is that we can directly represent this as a probabilistic circuit. Really, if you just look at how this distribution is defined, is that it's a bunch of little univariate distributions that are easy, just single Gaussians. And then we have a product node that combines them all into one larger distribution. So this product of smaller distributions will be a key ingredient in building probabilistic circuits. Okay, here's how you use them. There's still a computation graph, so right, so I want to plug in now some value for these 3 random variables. Then these little leaf distributions here, they tell me, for example, the density of the Gaussian at these 3 points. And then the density of this joint distribution is just the product of these little densities here. So in this case, it's 0.36, okay? So even though I combined these little leaf distributions here into a larger one, I still have my computational model, just like a neural network, that in a feed-forward evaluation tells me the probability of the state of the world. All right, so let's go maybe to our second ingredient for tractability, also one that Antonio already introduced, which is mixture models. So mixture models were clearly very useful in order to build interesting distributions. And Antonio already showed you this mixture of 2 Gaussians, which allows you to capture this orange line, which is more complicated than any of these individual Gaussians. So we'll try to do now a similar trick where we take this basic idea of a mixture model and we turn it into a probabilistic circuit. And so in this probabilistic circuit, we'll say that there's one component of our Gaussian, there's a second component of our Gaussian, both are over the same random variable, and we will mix between them using this convex combination. Okay, so it's a weighted sum of 2 other distributions that you mix together into a more complicated distribution. But again, it works just like a computation graph. I plug in maybe the height of a person, and my Gaussian says density 0.2 or 0.5 into the 2 different mixture components. I take the weighted average of these probabilities or densities, and I get my probability of evidence. Okay, so that's pretty straightforward. Now, those were just some of these models we saw earlier. How do we now build an interesting probabilistic circuit? Well, syntactically, it's really easy. All you have to do is take those sums and those products and stack them together in order to create very expressive distributions. Because as Antonio explained, just having one mixture model really is difficult. It's very difficult to fit your data because you will need many different components in order to fit some of those examples he showed. However, we will sidestep this question by just stacking things together. So what does it look like? This is a probabilistic circuit, just a single leaf distribution. This was also a probabilistic circuit. It's a mixture model. This is a factorized model. And then we'll just take a little bit of an inductive leap here. And now we can also take mixtures of products, and we can build arbitrary computation graphs that just alternate between products and sums in order to define this larger distribution here. And really, syntactically, that's all there is to defining this type of probabilistic circuit. I hope that makes sense. So let's maybe compare these things a little bit to what you may be more familiar with, probabilistic graphical models, things like Bayesian networks. So they look very similar. They're both graphs, right? Probabilistic circuits and probabilistic graphical models are graphs. The nodes in a, let's say, Bayesian network are random variables. Well, in a circuit, they're also kind of like random variables, but really they're more units of computation, just like in a neural network. So the edges in a probabilistic graphical model encode that dependencies, but in a circuit, they also give you a hint at how to execute inference on the circuit, how to compute the probability of evidence, for example. And so this means that when you want to do inference on these things in probabilistic graphical models, you have a very rich literature of algorithms. While in probabilistic circuits, it's much more simple. You just evaluate them in a feed-forward pass, sometimes also in a backward pass. I'll show you an example later. So these probabilistic circuits, they can really be thought of as kind of bridging between probabilistic graphical models and neural networks. Okay, so that's it. We just built this graph. You write down all of these layers of sums and products at some depth, build your neural network, and we're done. We have a distribution. Well, unfortunately, that's not enough. We have to think a little bit harder about what we need from this probabilistic circuit in order for it to be tractable for the queries that we care about. Okay. So the next part of the tutorial is, what are these structural constraints? What properties do we need from these circuits such that we can be tractable for various types of queries? And I will introduce two properties here, which were introduced by Adnan. And so these two properties will allow us to already make probabilistic circuits tractable for our query of interest, which will be marginals. So let me first introduce the properties, and then I'll explain how they help you do tractable inference. So first property is decomposability. So decomposability says that your products here, they need to have this property that they are multiplying distributions that are about disjoint sets of variables, right? So over here, I'm multiplying a distribution over x1 with 1 over x2 and x3. These are separate random variables. And so in a factorized distribution, that's how you do things. You multiply distributions that don't talk about the same random variable. So this probabilistic circuit here is not correct. It's not decomposable in that it's multiplying a Gaussian for x1 with another Gaussian for x1. And that doesn't really make sense mathematically. So the intuition is decomposability requires factorization over disjoint sets of random variables. Okay, this is a basic property for this, this to make any sense. Okay, second property. Oh, Ellie raised his hand. So I will allow you to talk, Ellie. Go ahead. You'll have to unmute yourself though. Not hearing you, Ellie.
Unmute. Hey, you hear me?
Yeah, now I hear you.
Two questions. You multiply probabilities, and you don't, and you call it this decomposable, and you don't mention the word independent. And essentially, this is just all the time I hear you say that x1, x2, and x3 are independent random variable first. Second, if multiplication is independence, what is can you give me probabilistic interpretation of addition? And aside from preserving sort of the mean is the weighted mean of the variable, I don't see a good interpretation. And the last thing that I want to ask, since here you say that this restriction on the network is paper with you and Darwish and whatever, who came with this idea of taking what is now looks like not copying, but it's a great idea to take you know what we know as a logic circuits, and instead of logic variable put probabilities. This is who came up with this idea first of these probabilistic networks.
So these are all great questions. So let me maybe answer them in order. So first question is, does this mean independence? So yes, if you have a fully factorized model, you're assuming that x1 is independent of x2. The reason why I hesitate to bring it up is because once we have a larger probabilistic circuit, then it doesn't really mean if we have a product node that x1 is independent of x2. It's a little bit more of a subtle independence statement that you can extract from the circuit structure. Something that if you know, for example, deseparation in Bayesian networks, it's a similar concept where you can infer independencies from the structure. But this is a very advanced topic that sadly I won't have time to get into. So yes, definitely you can think of this as a type of independence, but of course, once we build interesting distributions, we will certainly not have that x1 is independent of x2 because that would be a crazy assumption to make. Okay, so that's your first question. Then second question is, what does it mean to, if you had a sum here, a mixture model, what is its probabilistic interpretation? I'm not sure if I can really answer this for you. I mean, mixture models are something in their own right, but from a theory perspective, you can definitely think of it as being something like a low rank of your distribution, or there's some more more theoretical interpretations that can maybe help you understand what mixture models are. Then your third question is, who invented decomposability? So I believe Adnan did this in 2002. And so I was in high school then, so this was definitely not a paper with me. And the idea of, so definitely these concepts were introduced also for logical circuits.